All right. So today we're going to start talking about molecular orbital theory, and the molecular orbital theory is a it's a bonding theory, right? We have a way to think about how carbon bonds with other atoms and how carbon bonds with itself. It's in a sense an expansion of valence theory, right? You know that valence theory deals with orbital overlap. It deals with atoms sharing valence electrons in the outer shell, overlapping with one another, and then a bond being formed, basically being the optimal distance between the two atoms and a shared pair of electrons, right? So hybridization is an expansion of valence theory also, but molecular orbital theory kind of expands into um, more complex systems. So the questions that we're going to answer today and talk about is we're going to talk about what is an orbital, what's a molecular orbital, how to draw MO diagram, and then MO diagrams for linear pi systems, and other theories within molecular orbital theory. So other kind of perturbations of the idea of molecular orbital theory, right? So we all know about orbitals. We learned this first day of Chem, right? We learned about uh, S, P, D, F. We didn't learn about G, but there is a G orbital as well. We learned about that. And we learned how many electrons can fit into an orbital and how many uh, orbitals there are within a particular shell. So for the P orbitals, there's three P's, right? Because there are three different axes that the P orbitals can be on, right? Same thing for D. It's five of them because there's five different axes. And then we normally don't go past that. The only atoms on the periodic table that go past D are the lanthanides and actinides. So but and those are used. Don't get me wrong; they're used a lot in catalysis and things like that. But for the most part, we don't really go past the S, P, or D. All right. So an orbital is not real. It's an equation, and it helps us to determine the position of an electron um, in an atom. Right. And it's also used to calculate the probability of finding any electron of an atom in a specific region around the nucleus, right? So if you remember from Chem, the whole Schrodinger equation, H psi equals E psi, all of that is dealing with calculating the probability of finding that electron. All right. So we already talked about hybridization a little bit, right? You have atomic orbitals that add together to give you hybrids. And if it's a sp3 hybrid, then you know that it took one S and all three P's to give you a total of four hybrids. So the connection between hybridization and MO theory is that when you add together the atomic orbitals, you get the same number of hybrid orbitals. So if you add together an S and three P's, that's four total orbitals, then you should get four hybrids, so on and so forth. But if you have bigger molecules with a lot more p orbitals, then the hybridization model kind of breaks down. So you need a new model, a different model. And so that's where molecular orbital theory comes into play, right? So when you have for molecular orbitals, the difference is that you're not making hybrid orbitals. What you're making are molecular orbitals. So you have a atomic orbital and you add them or combine them together, then those atomic orbitals become molecular orbitals, right? And they describe again a region within a molecule where electrons can be found. So you have this linear combination of atomic orbitals. That's one method for combining atomic orbitals, LCAO, linear combination of atomic orbitals. Uh, and that's mainly where we are, or where we're gonna kind of hang out and talk when we talk about these extended pi systems. Uh, and you have in a molecular orbital, just like you have in an atomic orbital, in a valence shell theory orbital, a bonding and an anti-bonding orbital, right? So the model is hydrogen, right? So you have a hydrogen bond, so between two hydrogen atoms. right? So you've seen this before. Each atom brings one electron, and the bonding orbital, that's where the electrons are combined. And then the anti-bonding orbital, you can see where that's uh, what we would call destructive overlap. So in the bonding orbital, you have constructive overlap, where both orbitals add together. They share a pair of electrons between them. And then at the top, right, is destructive overlap. There's no electrons there, and the orbitals have uh, different signs, right? So that will be your anti-bonding orbital. Because in order for orbitals to overlap, they have remember an orbital is an equation. So in order for them to overlap, they got to have the same sign. You can't add them together if they have opposite signs, right? So this is illustrative of a MO diagram for the hydrogen molecule, right? So H2, right? This is carbon, right? And you can see right away it's much more complicated, right? A typical carbon-carbon bond in the second energy level, because the 1s is not included. You always the molecular orbitals are always your higher energy orbitals, right? And what you'll notice is that on this particular diagram, you see you have three P's and then the two S's, right? So 2s and then 2p, but that p is broken down into px, py, and pz. So for the 2s, you can see you have a bonding and anti-bonding, right? You have a sigma and sigma star. And then for the p orbitals, right, you have a sigma and two potential uh, pi's, right? So you have pi x and then pi y and then sigma 2p. You can see that right there in the middle, right? And then above that, those are your anti-bonding orbitals. So pi x and pi y would also have a pi star x and a pi y, or pi star y, right? Because anytime you have a bonding orbital, you also have to have an anti-bonding orbital, right? And then the sigma 2p is the same as the sigma 2p star, right? It's not the same. It's you have to have an anti-bonding. If you got a sigma p, then you got to have a sigma star p, right? So you can see right away that that gets a lot more complicated when we're talking about carbon-carbon bonding, right? Very complicated. It becomes much more convoluted when you look at the orbitals that actually have to overlap and where your bonds are coming from, right? And then they overlap in different ways, right? 2px and 2py, like the pi, the p orbitals that'll make your pi bond overlap on the edge, and then the sigma one overlaps head to head, right? So let me see if I can illustrate that. I think I can. Right. So if I have a P here, you have to excuse my drawing because I'm drawing with my mouse pad. This is what this means by edge, right? So the edge here and the edge here are going to overlap. If I have for the P, the sigma 2P, that would be head on. So it will overlap like this, right? So that's, let me fix that, sorry. So this will be 1P lobe here, and it will overlap with another P on this other side, right? So this is the head-on overlap, and then this is the edge overlap. So that's how your p orbitals and your make pi bonds by edge overlap, and then they make sigma bonds by head-on overlap. All right. Any questions so far?
No.
All right, let me erase that. All right. So again, if you look at this is for the pi molecular orbital, right? We're not really worried about the sigma, because with the molecular orbital, especially frontier molecular orbital theory, is mostly concerned with extended pi systems, right? So you can see the two p orbitals here overlap edge to edge, right here, and because of that, you're going to get pi bonding orbital, and then up here you get a pi anti-bonding orbital where the signs would be different and there would be destructive overlap. So there's no overlap between the lobes, right? So pi star is always non-bonding or anti-bonding, and then pi is bonding, right? So those pi molecular orbitals are going to overlap in this way to give you the two types of molecular orbitals, the bonding and the anti-bonding. All right, so the idea of taking the extended pi systems and developing a illustration or a diagram to show how they bond and which bonds which orbitals, molecular orbitals participate in bonding, which don't. That's based on this wave particle duality, right? So in 1905, Albert Einstein had a theory or concept that light can behave like a particle. And then in 1924, de Broglie says, well, electrons can behave like waves. So there's this wave, even though electron is considered a particle, a subatomic particle, there's this particle wave duality that allows us to think about electrons as both wave and particles, right? So electrons can have a wave-like particle and they can have a wave-like properties and particle-like properties. And if it has wave-like properties and we confine it to a small space, right, like an orbital, then we can say that we can think about electrons as waves. So you can express orbitals like standing waves, which we're going to talk about in a second. So electrons that are confined to a small space are going to have wave-like properties, and that allows us to develop these really simple molecular orbital diagrams for extended pi systems, because that's where we're going with all of this anyway. All right, so this is the standing wave theory, where you have in the first harmonic, if you remember this from physics, excuse me, first harmonic, the wave never passes through zero. And then in the second harmonic, it passes through once. The third, if you notice, the wave's frequency is increasing as you go up in energy. Because you can see on the left side of the screen, energy is increasing in this direction, right, vertically. So every time you have an increase in energy, you also have an increase in the frequency of the wave, and that's going to determine how many times that wave passes through zero. All right. So the standing wave theory is what we use to describe molecular orbitals for extended pi systems, right? Because of the fact that the electrons have both particle and wave-like properties, we can describe them using descriptions or depictions that are, normally reserved for describing waves. All right. So if you look here, right, this is basically for these linear conjugated pi systems, which we're going to talk about. This is the depiction for those types of systems, and I'm gonna show you. Yeah, we're gonna talk about 2 pi, 4 pi, and 6 pi, right? So, and when we say 2 pi and or 4 pi or 6 pi, we're talking about the number of pi electrons or the number of electrons that are in p orbitals, right? So for a 2 pi system, you have that's depicted right here, right? Where you have a two p orbitals overlapping. So that's going to create two molecular orbitals. So each one of these is what we call a molecular orbital. And you probably, if you took my organic 2 class, you probably remember all of this, or at least vaguely remember it, right? So that 2 pi system, where you have those two molecular orbitals, right? Note if you notice, we're going to talk about this more on the next slide, but if you notice, this is your bonding, and then this would be anti-bonding, right? Bonding is always where the orbitals have the same sign and they overlap constructively, and then anti-bonding is where they overlap destructively. So it's a 2 pi, 3 pi, 4, 5, and 6. All right, so let's talk about the 2 pi system. All right, so that would be a basic alkene, right? Any double bond can be classified as a 2-pi system. It's not conjugated to another double bond, so we don't have to worry about the extended overlap or compression between the two carbons with a sigma bond. None of that. That'll be for the 4-pi. We'll look at that. But for the 2-pi, right? Remember, each one of these carbons has a p orbital on it in the pi bond. So it's a p orbital here and a p orbital on the other one. And again, excuse the sloppiness of that. I don't have a touch screen. So these two p orbitals, that's two atomic orbitals. And then we add them together, we should get two molecular orbitals, which we do, which is shown down here. So you have a molecular orbital here, and then you have a molecular orbital here. Those are the two molecular orbitals that we get. All right. And so because of that, we can look at these molecular orbitals and describe them like waves, right? So you have here, the wave never passes through zero, right? Based on the standing wave theory. And so if that's the case, then the sign of the orbital should never change, which is why both of these orbitals are have the same, the color is indicative of the sign. So they are both basically shaded, right? And so that means that they both have the same sign. So this is going to be constructive overlap. So that means that this is going to be a bonding orbital. Right? It's going to be a bonding orbital. All right. And then up top, you can see here, right? So the wave, the wave here never passes through zero. And then up top, it passes through once, right? So when it does that, excuse me, you'll see the sign of the orbitals change, right? You see how this is shaded and this is unshaded, right? And that sign change means that the wave has passed through zero. So this is bonding, and so this is where I'm going to put my two electrons. Because keep in mind, this is a 2-pi system, so I'm only working with two pi electrons. So I'll put them both here, and this is in the ground state. If it was excited state, then it would be different. I could move up one electron up, but with it being in the ground state, I'm going to fill up the low energy orbitals before I put any electrons in the high energy orbitals based on Hund's rule. All right. So with that being said, this is bonding. This is anti-bonding. I'm just going to abbreviate it. All right. So anti-bonding, no electrons there. And then we call this the pi orbital. And then we call this anti-bonding pi star. Right. All of this is a consequence of those two p orbitals overlapping. And this is how we can explain the reactivity of pi systems, right, using molecular orbital theory. All right, any questions about this 2-pi system? All right, let's go. Let me clear this out and go to the next slide. Right, so the allylic system is it's a 3p orbital system, even though it has it's a type of 4-pi system because you have 4 pi electrons total, but it's a 3p orbital system, and that there are 3p orbitals that are overlapping, right? So you can think about that here, right, where that lone pair on carbon is actually in a p orbital, uh, giving that carbon a tetrahedral geometry, right? So all of these are considered allylic systems, right? And if you look at the molecular orbitals, so you got p here, and then got a P here, and then another P on the other carbon. Right, so that's where your 3 atomic orbitals come from. So if you add those together, you're going to get 3 molecular orbitals, which are shown down here. All right. And then so again, if you follow standing wave theory, the 3 p orbitals are in the lowest energy level are not going to change signs because the pattern for the wave never changes, right? So it's always no nodes, 1 node, 2 nodes, 3 nodes, 4, so on and so forth. So in the bottom, the lowest energy level, there are no nodes, right? Then the wave never passes through 0. And so because the wave never passes through 0, all your orbitals have the same sign, right? And then you go to the next energy level and you can see that the wave passes through 0 once right here. And what that does is it nullifies one of your orbitals. This is really important for reactivity because what this means is that any allylic system is only going to react through the termini, right? It's only going to react through, like say for instance, this one, it's only going to react through nitrogen or this carbon right here, but it'll never react through the central carbon. And that's based on the molecular orbital diagram shown here. So that's a way to explain why the central carbon never takes place or never participates in a reaction, and it's because of this in the second energy level, which is where it will react from anyway, because you always react from your higher energy levels. Uh, there's no p orbital here, right? It gets canceled because the wave passes straight through it. All right, and then third energy level is here, right, where you can see the wave pass through twice, and so because of that, you get alternate your orbitals. The signs on your orbitals are going to alternate, right? So you'll be shaded here, unshaded here, and then shaded here. All right, is that making sense?
Yes.
All right. So all of your allylic systems are the same, right? They have the same exact MO diagram. They're all 4-pi systems, but they're 3p orbital systems, right? Uh, and they follow the same pattern. And then this is again, when you think about that second energy level, you can think about also each one of these having the potential to do resonance, which also explains the reactivity, right? So I can take this pair of electrons and push it here, and I can take this pair and push it here, right? And then I get this resonance form shown over here. And all of these can participate in resonance. All right, so that's an example of a 4-pi 3p orbital system or an allylic system. All right, let me. All right, so when you get to a more complex system, like a 4-pi system, like 1,3-butadiene, which is shown over on the right, right, you can see it's the same idea, same concept. No nodes, 1 node, 2 nodes, and then 3 nodes. So your 4-pi system, the MO diagram is going to look just like this. You have 4p orbitals because you start with 4p orbitals. You're going to have 4 different molecular orbitals, right? And you can see here, 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 and here. Those are your 4 molecular orbitals. And the way that those orbitals combine with each other, that's another way to think about uh, the overlap, right? They can combine in 4 different ways. If you got 4 atomic orbitals, there are 4 different ways that those orbitals can overlap and be depicted. So that's what you have here, right? And then you got 4 pi electrons because you got 2 pi bonds. So you're gonna insert your electrons here and here, and then just to introduce another idea or another concept dealing with molecular orbital theory, right? This orbital right here, this molecular orbital is what we call the HOMO, right? Highest occupied molecular orbital. That's this one right here, right? And then above it, the lowest unoccupied molecular orbital, or LUMO, is here, right? And this is in the ground state. If I irradiate this with UV light, then I'm able to move to the excited state, which is here. And the excited state means that I'm going to change the reactivity. It's not going to react the same, and the outcome of the products is not going to be the same, simply because you have an electron now here. You have a new HOMO, and so that's going to change the reactivity. All right. So where you see this play out is in the reactions. 4-pi systems are known for doing like Diels-Alder reactions, 4+2 cyclizations, and they're also known for doing addition at conjugate addition. If you add like HX to the conjugated diene, so on and so forth. So the excited state and the ground state changes the reactivity, and it changes the orbitals that are reacting, right? If you're HOMO, the reason this is important is because sometimes your diene, in this case, may be the nucleophile. And if it's acting as the nucleophile, that means that your HOMO is reacting through the HOMO, right? And if it's reacting as the electrophile, then that means it's acting as the LUMO. Type that in. So if this 4-pi system is acting as a nucleophile, then it's going to react through the HOMO. I'm trying to get it. All right. And if it's acting as an electrophile, then it's going to react through the LUMO. Right? If it's accepting electrons. Right? And that's for any of these pi systems. They can if they are reacting through the LUMO with the HOMO of another system, then they're going to react through they're acting as electrophiles, right? Because electrophiles accept electrons. If they're acting as the nucleophile, then the HOMO of one system is going to overlap with the LUMO of another system. All right, so we're going to talk more about that later. All right, so let me clear this off. You see the same with the 6-pi system, and we're going to talk about. Let me see if that's on here. Do I need to? Yeah, I'm gonna talk about that later. All right. So you see the same thing with 6-pi, right? You have 6 p orbitals, so you're gonna have 6 molecular orbitals, and they're depicted here. It follows the same wave pattern, right? 0 nodes, 1 node, 2 nodes, 3, 4, and then 5. And you can do this for any extended pi system. You can draw the molecular orbital diagram for it. It doesn't matter how many p orbitals there are. If it's conjugated, you can draw the MO diagram for it. And I kind of missed out or kind of skipped over that talking about conjugation, right? That's why this is possible, because all of these p orbitals overlap and form one big unit. Those sigma bonds in between the two sp2 carbons here and here get compressed because of the electronegativity of the sp2 carbons. So those bonds get compressed, and then when that happens, all those orbitals overlap, and you make this big giant pi system. So that's why we're able to draw these MO diagrams like this and include all 6 of those orbitals, or however many p orbitals are present. Right? Again, you have your ground state here, HOMO and LUMO, and then you have your excited state where now the HOMO is, that's a typo, the HOMO should be here, and then the LUMO should be here. Let me fix that right quick. And I'll fix it on the actual slide before I upload it. All right, so that's the HOMO, and then this will be the new LUMO in the excited state. And the way you get to, again, the excited state is to irradiate that compound with UV light, right? Add energy to move that electron from one orbital to the next. All right. And this is it again, 135 hexatriene is an example of a 6-pi extended conjugated system. Right. And with the a cyclic system like benzene, it's going to be a little bit different because all of your bonds are the same length. The pi bonds and the sigma bonds are all the same length. And so when you draw the MO diagram for it, it's actually going to be, right, you see here you have no nodes, right? And then in the second energy level, where you have 4 of your 6-pi electrons, you have a node cutting here and a node cutting here. So that's the symmetry of the ring, right? So you have one node here and then one node here. The thing about benzene though is it's notoriously unreactive, right? And so, but this does help us to understand whether you're doing nucleophilic aromatic substitution, where you're adding in the ring is acting as a nucleophile, then it's going to react through here, right? And that'll help to explain like the ortho and para directing effects and all of that. And then up here, if you're doing electrophilic aromatic substitution where the ring is acting as a nucleophile, then that helps to explain that too, because the that change the directing effects change based on whether you're doing electrophilic aromatic substitution or nucleophilic aromatic substitution. All right. But again, you see here in the anti-bonding, right, you got 2 nodes, just like in the diagram, 0 nodes, 1 node, and 2 nodes. But the symmetry and the way the ring is cut is different, right? You see on here, this is the symmetry here, and then on the other side, the symmetry is here, right? But the idea and the concept doesn't change, right? The fact that you can treat this as a with wave-like properties, that it has wave-like properties, and you can treat it like that. All right. And then in the top, you're gonna have 3 nodes right here, and you can see how the ring is cut symmetrically. And I didn't mention that on the other examples too. When you put the nodes in, they have to be symmetrical. Unless it's an odd number of orbitals, then it's still symmetrical, but that means that one of your orbitals is gonna be canceled out if a node falls on top of it. But for your um, even numbers like the 4-pi, the 6-pi, 8-pi, so on and so forth, right? The orbitals, after when the wave passes through 0, it has to cut those orbitals symmetrically, right? So if it passes through once, and this is a 6-pi system, then it's got to fall right there in between the first 3 orbitals and the other 3 orbitals. All right, and the same thing for here, right? If it's cutting twice, it's got to cut symmetrically. All right. Right, and you can see this is just another example of a 4-pi system. It's a cyclopentadienyl cation, and it's the same idea, right? You got 2 electrons in the lowest energy level, and then you got another 2 electrons that you put in the next energy level, right? And again, if this is reacting as an electrophile, it's going to react through this anti-bonding orbital, right? So you can see right here that cation, it's going to be an empty orbital, and you can see that that's a direct, it can react directly from there. But if you do resonance, you can also see that the the cation can be shifted around the ring, right? So it can be here, which is, you can look at it reacting right here, or it can be here, which you can see it reacting from here, right? So again, the idea is that you can use MO theory to help to determine like how POS systems react and where they react, and you do that based on the standing wave theory. And this is just a cyclopentadienyl radical, same symmetry but different reactivity. And then the anion again, same. You can see the same symmetry and but different reactivity. And this is going to be reacting as a nucleophile. So you can see right here is either going to react through this carbon, or if you push the electrons around, you can see that the carbons on the corners can also react if it's reacting as a nucleophile. All right. So now let's think about how we can use this to our advantage, right? We know about these homo-lumo interactions, and we know that when two molecules that are reacting through molecular orbitals come together, right, they're going to react. If the nucleophile is going to react through its homo, and the electrophile is going to react through its lumo. And so there's this concept of what we call homo-lumo perturbation, right? Because one of the things about doing reactions between the homo and the lumo of two molecules is you want the homo to be as high in energy as possible so it can reach the lumo of the other molecule. Go ahead, somebody has a question.
No, sir.
Oh, okay, all right. So you want your HOMO to be higher in energy, as high in energy as possible, and you want your LUMO to be lower, as low in energy as possible, so that you can get good overlap. Because the HOMO LUMO overlap is going to determine how fast the reaction is and how well the reaction occurs. So the way that you do that, you can increase the energy of the HOMO or decrease the energy of the LUMO depending on your substituents. So you can see right here for this allylic cation, I have a POS system right here, but in with that POS system, what I've done it by attaching this carbocation is I have attached an electron withdrawing group, something that's going to delocalize electron density, right? So what that's going to do is drop the energy of the LUMO down compared to the middle structure. Can you see that? So if I have just a regular simple pi bond, you can see right here the HOMO is here and the LUMO is way up here. But the minute I add an electron withdrawing group, it drops the energy of the system. And in doing so, you drop the energy of the HOMO and the LUMO. Right? So electron withdrawing groups or electron acceptors lower the energy of the HOMO and the LUMO. What that does is that makes this a better electrophile. Because if I'm reacting through the LUMO with the HOMO of a nucleophile, then I want my LUMO to be low in energy. Because I want the nucleophile HOMO to be able to reach it so that they can overlap, so the orbitals can overlap. Right? And if I compare the middle structure to the allylic anion on the other side, you see what happened, right? My HOMO actually increased in energy because I put a donor in the system. Right? So if I add a donor, that's going to make the HOMO energy go up. Right? So by adding a donor, I can push the HOMO up. Right? And what that does is that makes that system now more nucleophilic because the HOMO is higher in energy, and then it can overlap with the LUMO of some other compound, right? Is that are you following that?
Yes.
Mhm. And then again, what we're comparing the cation and the anion to is the unperturbed system with no additional substituents, no electron withdrawing groups, no donors, just it's just there. All right. So that concept of perturbation also helps me to understand reactivity, right? It helps me to understand why a POS system that has a electron withdrawing group attached reacts faster than one that doesn't, or why a nucleophile, if the POS system is acting as a nucleophile, why it reacts faster if a donor is attached, and as opposed to one that doesn't have a donor, right? So this is basically helping us to understand the reactions of POS systems, right? So again, it's dictated by this homo-lumo overlap. And if you didn't get a chance to download that Scudder book, Electron Flow and Organic Chemistry, all this is in, like, I want to say the first or second chapter in that book. But all of your POS systems are dictated by this homo-lumo overlap. Again, so the, if you close the gap between the homo and lumo, that's going to make for a better reaction. You can see right here the homo of A overlapping with the lumo of B. Look at the gap between the homo and lumo. It's a huge gap. But if I add a electron withdrawing group to A, right, that's going to change everything. It's going to bring the homo and lumo down, right? And if I add I'm sorry, if I add a donor to A, right, it's going to make the homo and lumo go up compared to A over here. You can see that the homo is a little higher in energy. And then if I add an acceptor to B, it's going to bring the homo and lumo down. So now the orbitals I want to overlap, the homo of A and the lumo of B, are closer in energy. And the closer that gap is, smaller that gap is, the better the overlap is going to be. The better the overlap, the more reactive those two species are going to be with one another. All right. So we'll talk about some examples of that probably on Wednesday, just to clarify and make it make sense. Right. And then if you look here, do I want to do that? I'm gonna stop here. I'm not gonna start pericyclic reactions. I'll stop there, and then we'll look at some examples of homo-lumo overlap for these perturbed POS systems, and then we're gonna look at some pericyclic reactions like Diels-Alder and electrocyclization. But we're gonna look at them from a molecular orbital standpoint. But we'll do that on Wednesday. So I'm gonna stop right there. Are there any questions?
No.
No, sir.
All right. And again, I'm going to check to see if this PowerPoint is in Blackboard, but if not, I can email it to you since it's only uh, the three of you. I can just put it in. Sam, did you get your email address squared away?
Yes, sir. I finally got it fixed.
Okay, great. Yeah. All right. So I'll email this